So this is a lab demonstration for ECE 1175, lab number 4 for Yinhao Qian. So let's try to go over the section number 1. I have rewritten all the code that is different from the provided template code. So let me show my code first. So I've written everything. The controller here, Boolean is RMS, is controlling which algorithm to use. So for the section number 1, we're going to use the RMS algorithm, and for the section number 2, we're going to use the EDF algorithms. So first, we're going to set the RMS Boolean to true, and also we're going to try to set the parameter for both processes to the correct value. I've already set the process number 1 having an execution of 10 and a period of 25, and also a process 2 having an execution time of 15 and a period of 60. And we're going to see the timing diagram for the scheduling from the 0 second to 300 second. So let's try to compile the code. Okay. So basically what it means is whenever there's a dash line here, it means the process, this process is not running the CPU. And whenever there is a pound sign here, it means this process is running the CPU. And it's not possible for both processes to run in the single core CPU at the same time. So here's the result. And we can also see the utilization rate here is 65% after 2 processes has been appended to the queue. That's what happens. Now, let's try to change the process parameters a little bit by changing the execution time and the period to a new value. Let's change the execution time here to 20 and 50. And execution for process 2 is 35 and 100. Maybe let's try to see the time between 0 second to 100 second. Save the file, exit, recompile the code. Sorry, wrong file. And running the code, we can see this is what happens. And we'll now move to section number 2. Let's change the code again to change the way our algorithm and also the execution time and period of our new processes. So first, let's try to change the algorithm from RMS to EDF. And then, let's try to get some new processes. So the first one is going to be 10 and 20. And here's going to be 50 and 25. Save the file, recompile the code. And try to run the code. And the last part of the section 2 requires 25, 50, 35, and 80. So let's change our parameters to that. Oops, sorry. And now let's compile the code. And running the code, we can see the timing diagram here. Now let's move to section number 3. It will demonstrate a process priority inheritance. So let's draw the code first. It's s2.c. I definitely made some reference from the example code, but my code is essentially different. It's simpler. I created 3 processes, with the first process having a priority of, with the first priority of 10, and with the second process having a priority of 7, and the third process is having a priority of 4. And the main process will have a very high priority of 90. Okay, let's try to run the code. Let's first try to compile the code using the LP thread. And let's try to run the code. Since my Linux right now is set to only 1 core of CPU, so I'm going to skip the task cell command because it is not necessary here. So let's try to run S2. Okay, so we can see first the thread 3 is trying to run and trying to attempt the lock. And then after thread 1 is running, when the thread 3 is running, thread 1 has been released with a priority of 10, which is higher than 4. And then thread 1 is trying to access the mutex lock. And then the thread 2 is also released and then trying to access the mutex lock. But as soon as the thread 3 is unlocked, which means the lock has been released, it is thread 1 instead of thread 2 who will have the access to the mutex lock. And then the thread 1 will also do some stuff, and then after thread 1 will unlock the mutex lock. That is when the thread 2 will have the opportunity to use the mutex lock. And then after running thread 2, thread 2 will then unlock the mutex lock, and then everything will be finished. And that's my demonstration, and thank you very much.